Okay, so welcome to the new normal of social distancing and lecturing this spring. Okay, so going to do a couple kind of review lectures that'll bring you up to speed, kind of refresh you of what we were talking about before spring break, especially since I was gone right before the break started. So today we're going to talk about microstructural deformation mechanisms. And this kind of begins part 2 of our course. So, up to now we've discussed the forces that produce structures in strain and how stress translates to strain. And now we're going to talk about the structures themselves, which include microstructures, faults, folds, joints, fabrics, and shear zones. So to clearly understand the range of structures that we see in the scale of individual outcrop and enhanced specimen, we have to draw our attention kind of to the interior of rocks and mineral grains and see what's going on inside our materials. Okay, so let's see how well I can manage this new system. I'm going to switch over to the doc cam, okay? And I'll try and write as much as possible so that way you can still follow along actively in these videos. You're not just watching, a video. Okay, so we're going to talk about deformation mechanisms. Okay, deformation mechanisms are processes that permit rocks to deform at the microscopic and atomic scales. And the resulting fine scale structures are that result, or what we refer to as microstructures. So let's write down that definition. Okay, are processes that permit rocks to deform at the microscopic and atomic scales. The resulting fine scale structures are what we refer to as microstructures. Okay, so there are a diverse array of deformation mechanisms and processes that operate at the micro scale, which when we're saying microscale, we're talking about atomic to thin section scale, which are going to be what facilitates deformation. Okay, and so we're going to list the main deformation mechanisms, and it's going to take a couple of these video lectures to kind of get through these because we're going to talk about a little bit of context first. Okay, so the main deformation mechanisms. We'll make a list here. Okay, so we have microfracturing, we have frictional sliding, we have cataclasis, we have mechanical twinning, and kinking. And then we have a couple different types of creep. We have diffusion creep, we have dissolution creep. Let me move this to a better spot where you can see this a little better. Okay. Dissolution creep. And dislocation creep. Okay, Okay, and we'll get to these in the next video. Microfracturing, frictional sliding, and cataclasis. And these, and sort of kind of mechanical twinning and kinking as well, they sort of operate in the brittle realm and have brittle, more brittle behavior, brittle deformation. Whereas our creeps are going to be kind of our more ductile or plastic deformation mechanisms. Okay, so we'll look at these mechanisms in detail in a minute, or maybe by the next video lecture. But broadly, let's ask the question: why do we start small when we're thinking about structures? And really, the reason why is that these processes at the micro scale, they dictate the formation and behavior of larger scale structures. Okay, so let me switch again back to our PowerPoint here. Okay, and the Himalayas are a good example of, this. Okay, even though this is a mountain belt with abundant macro to outcrop to large scale structural features, one of the important ways that researchers approach understanding the formation of this origin is through microstructural analysis. So we can look at things at the micro scale to understand the macro or plate boundary scale, in fact. Okay, so jumping back to our doc cam, let me move this page out of the way. We're done with that. Okay, we're going to talk about some micro scale features. Okay, so the first thing we want to talk about is a crystal lattice. Crystal lattice. So crystal lattice is a repeating array of atoms that are held together by bonds. And the position and spacing of the atoms within lattice are very systematic and kind of dictated by the chemistry and the chemical bonds themselves. Okay, so a repeating array of atoms held together by bonds. The position and spacing of atoms within the lattice are systematic, are very systematic. Okay, so let's make a little drawing here, okay, of a crystal lattice. Okay, and we're gonna have these little spheres here. Those represent atoms, ions, molecules, and the lines between them, okay, are going to be our bonds. Okay? And we'll talk a little bit more about bonds here in a moment. Here's a very crudely drawn cube. Okay, there we go. And okay, so our lines, those are our bonds, our chemical bonds. Okay, so a unit cell, something called a unit cell, Unit cell is the smallest known repetitive structure composing the crystal. Okay, so similar, so here's our unit cell in this depiction of a crystal lattice. Okay? The smallest known repetitive structure composing a crystal. So our crystal as a whole repeats this pattern, okay, over and over and over. And now, recall, okay, we got a new drawing here. Move this up a little bit. Okay, recall from our discussion of rock deformation experiments. Okay, that rocks are different deformation mechanisms, right? So here's our graph. We have this graph of differential stress, okay, which was sigma 1 minus sigma 3, or the difference between the two, and strain, okay, which we depicted as E, the extension of our material. Okay, so in our rock deformation experiments, we had certain type of behaviors of material, or models for material behavior. One of them was elastic behavior, one of them was plastic behavior, and the final was viscous behavior. Okay, we care mostly about elastic and plastic behavior. Okay, so recall with elastic behavior, looks something like this. Okay, and so similar to rocks at the crystal lattice scale, okay, down at this scale, okay, applied stress, okay, applied differential stress, which is this graph, produces elastic deformation, okay, which can manifest as compression or dilation. I'll show you a diagram of that here in a minute, until we reach a yield strength, right? So recall, yield strength is the definition of yield strength is the differential stress at which material departs from elastic behavior to plastic behavior. Okay. So that would be this point where our material starts to kind of roll over. Okay. And recall too that elastic deformation or elastic behavior, okay, is defined by basically stress. Remember, sigma is our symbol for stress, is proportional to strain. Okay, okay, and strain, okay, E is recoverable if we let off of the stress during elastic behavior. Okay, so once we get up to our yield strength, the material starts to behave plastically, and now we can't recover any of that strain from our crystal lattice, and at some point it fails. Okay, so let me switch screens again here, back to our PowerPoint. So again, we have our, if you can see my mouse here, okay? Let's see what happens if I try to do this. Pointer options, there we go, laser. Okay, so you can see, okay, here's our crystal lattice, here's a unit cell, here up here on in figure A, okay, we have an undeformed crystal lattice. And if we subject our crystal lattice to stresses, it can respond elastically, meaning it can dilate or expand. And if we let off, as long as it's behaving elastically, if we let off those stresses, it recovers its original shape, okay? So all of the strain is recoverable. So for example, B here, okay, this illustrates the elastic response to an increase in confining stress. In this specific case, it would be hydrostatic compression, which means that we have equal stress directed in all three dimensions in our object. Okay, the bonds shorten, okay, and the crystal decreases slightly in size, and the energy, okay, that we are imparting into our crystal by stressing it, it's stored as potential energy, as in a compressed spring. Okay, so we let off that stress, the material will expand again back out to its original shape. Figure C here shows the elastic response to an imposed tensile stress, or basically pulling apart the crystal lattice. And the amount of strain shown here is actually greatly exaggerated compared to what's possible in real geologic media. Typically, most crystals are only able to basically be strained by 1% before they elastically fail or reach their yield strength. Okay, and then down here in figure D, I suppose, figure D, okay, that shows the elastic response to shear stress. We kind of kinked over the crystal lattice, right? Okay, so ultimately, our yield strength, again, which is the point at which we depart from elastic behavior to plastic behavior, okay, the amount of stress that it takes to do that, is governed by the strength of the bonds between our material here. And when that strength is exceeded, we end up having permanent strain or permanent deformation. The shape of the crystal lattice is inalterably changed. Okay, so when tensile stress is exceeded, we have a row of bonds that will be severed. Okay, and the crystal will break. And the break can be irregularly crossing the lattice, okay, producing a fracture and completely breaking the plane of bonds. Or it might follow a crystallographic plane of weakness, producing a mineral cleavage. We'll talk a little bit more in detail here in a moment. Okay, it all depends on the internal structure and the relationship of the direction of stresses to the internal structure, the way that the crystal lattice is built. And similarly, if the magnitude of strain, of shear strain, exceeds the elastic limit of the crystal enough to shift, either a fracture will develop or the lattice will slip and glide, which we see here in this depiction. Okay? And when slip occurs, or slip does occur when atoms on one side of the crystallographic plane suddenly shear with respect to the atoms on the other side of the plane. And after slip, the undisturbed part of the crystal remains intact. So everything on this upper side of the slip plane and everything on this lower side of the slip plane, they remain coherent and undeformed. We simply slip these pieces past each other. Whereas the crystal itself is permanently deformed where the shift occurred. Okay, so just like we talked about, the stress required to break a rock, okay, to reach failure, okay, to reach its yield strength. I should label this. Or to cause frictional sliding, right? So when we get down here, down to this level, now we're causing frictional sliding. Okay? Whether a crystal deforms by a discrete fracture, okay, actually breaking the bonds, or by slip along a crystallographic plane, it depends on whether or not the stress required for the fracture is greater or less than the stress required to slip. In other words, if it takes more stress to fracture the crystal itself or break the bonds, okay, then the lattice is just going to deform by slipping on either pre-existing crystal faces or crystal faces that have been formed during this stressing event. And when there's more stress required to slip, okay, if the friction is too great on say the boundaries between crystal faces, or they're not oriented favorably for slip, the lattice is going to deform by fracturing and by breaking bonds. Okay, so intuitively, slip systems are intuitively slip and fracture direction, as well as the overall yield strength of a material, okay, are profoundly influenced by crystallography and the bonding itself in the lattice. So in some cases, a suitably weak and suitably oriented crystallographic plane is the preferred mode of inelastic deformation. Okay, so let me pull another fresh piece of paper here. Okay, and you can write down a couple of definitions here. Okay, so just a couple words we threw out there. Okay, slip plane. That's the crystallographic plane that slips. And slip system, okay, that is the line or lines of slip within the slip plane. In other words, it's basically what direction the material slip. Okay, so intuitively, right, the slip direction and the slip plane are often going to form along cleavage planes or planes of weakness, basically where the bonds are the weakest already. Okay, so a good illustration of that would be in the crystal system for example, biotite and olivine. Okay, so in biotite, the plane of weakness, this cleavage plane, is in the 001 plane in our Miller indices, and for olivine, okay, it's a plane actually perpendicular to the plane of weakness in a biotite. So the degree of slippage or the development of cleavage in slip planes is intuitively related to the type of bonding that we have. Okay, so we can kind of rank our sorry, I lost my place. Okay. 1 second. Okay, so the kinematic character of a slip system is analogous to more or less shearing a microscopic set of playing cards. Okay, so if we can think about that, sorry, I lost my place there for a second. We have a deck of cards, right? Okay, and each card remains undeformed. Each one of these doesn't get bent or slipped, okay? But the space between them is slipping if we kink this thing over by shearing it, right? Okay, so if we zoom in again on just one boundary between these two, okay, we see it looks something like this between cards. Okay, just a little bit of slip between our cards here, okay? But tiny amounts of slip between each adjacent card can basically dramatically alter the shape of the entire deck, right? So if we imagine, okay, that was just looking at one little boundary between two cards. If we have the entirety of the deck, okay, the entire shape of our deck of cards is altered quite a bit, okay, by each of these kind of some amounts of slip on each slip plane between minerals. Yeah, so this whole thing is kind of our sum of these little increments of slip. Okay, so for example, yeah, and the degree of development of cleavage and slip planes, it's related to the type of bonding. Okay, so our types of bonding are ionic, covalent, and metallic. Okay, so for example, if we look at a material like halite, which we have, which is we basically have ionic crystals, okay, or ionic bonds in a cubic shape. So positive and negative ions are alternating in the lattice. Okay, so if we draw what a halite crystal looks like, we're just going to draw some elements like this. Okay, so like I said, it's we have positive and negative ions alternating the lattice. Positive, negative, positive, negative, positive, negative, positive, negative. Oh, that's positive. Negative, positive, negative, negative, positive, negative. Okay, and just by nature of these ionic bonds, okay, the easiest slip direction will generally be in the direction that doesn't bring ions of like charge into close contact, right? So if we slipped this whole thing this direction, okay, and move those crystals that way, it would put a negative, let's see, it would put a negative or positive next to a positive, and this crystal doesn't like to do that. Okay, so the easiest way for it to do that is to break along diagonals like this in ionic materials that are cubic like this. Okay, and it would slip this way, and this would be the slip plane. And this would be the slip direction. Okay, so this generally applies actually for cubic crystals with any ionic bonding, say. So the cubic crystal will slip within the one, if you recall Miller indices, the 110 plane along a direction or the 110 diagonal. Okay, so in reality though, many minerals have complex crystalline structure, much more complex than halite here. Okay, and halite has perfect cleavage because it's kind of got this simple ionic bonding to it, and it's easy to slip along this diagonal. Okay, so when you break apart halite, when you smash it and it cleaves perfectly, it's breaking along these slip planes. Okay, so in reality though, many of the rock forming silicates, for example, they can possess much more complicated atomic arrangements. They possess covalent and ionic bonds essentially in the same crystal lattice. And the general rule is this, that complex silicates will fracture or slip along planes that break the weakest bonds or the fewest strong bonds. So cleavage surfaces and slip surfaces will tend to avoid breaking bonds between silicon and oxygen, which have a mixed covalent ionic character and are especially strong. Okay, so quartz is composed entirely of silica and oxygen, and is very strong because the slip must break through these tough silicon-oxygen bonds. Whereas phyllosilicates, which are micas, on the other hand, are relatively weak, and they slip easily along the 1-0-0 plane because they have a weak ionic bond that's holding together layers of cations between these double sheets of strongly bonded silica tetrahedra. Okay, so I suppose the last thing I want to leave you with in this video is I'd just like to say one last thing, I guess, about slip planes and slip systems in regard to bonding. And that's the minerals with low yield strengths generally can accommodate simultaneous movement on multiple slip planes, okay, permitting ductile flow of a mineral. So think back to the deck of card examples here, okay? And now imagine we have a rock with a whole bunch of aligned micas. It will potentially deform with ductile-like behavior by permitting simultaneous slip on all of these surfaces, so on multiple mica surfaces at the same time. Okay, and so bonding is really important, the overall strength of the bond. Okay, and we can kind of rank bonds in terms of, generally speaking, how strong they are and how strong a material will be or a crystal lattice will be depending on the type of bond it's held together with. Okay, so our rank of bonds is as follows. Covalent are the strongest. Okay, they're much greater than ionic bonds, and material that are obviously covalent ionic bonds, okay, they're stronger than ionic bonds alone, okay, and covalent and ionic bonds are both much stronger than metallic bonds, and you know this intuitively. Say, for example, you take a coat hanger, okay, and you bend it. You can bend it ductily, or it deforms plastically at room temperature. It doesn't really deform elastically, right? So the way metallic bonds hold the crystal lattice together, they're just generally weak. We're going to call these weak AF. All right, and you all know probably what that means. Okay, so one last thing, I suppose, okay, is that bonding can affect the strength in yet another way. Okay, so by influencing the chemical properties of the mineral, so in particular solubility. So minerals that are easily soluble or chemically reactive, okay, things like halite, or which is soluble in water, or things that are chemically reactive, things like calcite, which are reactive to acids and dissolve. They generally have low yield strength. And they do so by playing essentially disappearing air. They can dissolve and migrate under the influence of directed stress. Okay, so we're going to leave it there in this video. Come back and please keep up with the next video. And we're going to go ahead and stop the recording here.